here I'd like to go over an introduction to IEEE floating point numbers. This is just for review. So first, there are a few different kinds of numbers, of floating point numbers, and we can recognize each one by looking at the exponent. So let's assume that we have a 9-bit representation. The first bit is always going to represent the sign. And I'm going to say we're going to have 3 bits that represent the exponent. I'll write that as 0, 1, 0. And then the remaining bits, in this case 5, are going to be the fractional bits. So the 3 kinds of numbers that we have to work with are, we can recognize by looking at the exponent bits. If they're all zeros, then the number is a denormalized number. If the exponent bits are all ones, then we have a special case. And if it's anything else, then we have a normalized number. So that's how we recognize the 3 different kinds of numbers. So the number I've written here as an example would be a normalized number. So let's go through the rules for the normalized numbers first. So we have these 3 parts. The first bit is the sign. A 0 represents a positive number, a 1 represents a negative number. I'm going to refer to the exponent bits just as the exponent bits, I guess, but the value of them I'll kind of call the bits. So in this case, 0, 1, 0, that would be a value of 2. And then we also have the exponent value, which is 2 to the power of the bits. All right, that is 2 to the bits. Then we have the fractional bits. Oops. In our case, 1, 0, 0, 1, 0. And for a normalized number, there's an implicit 1 point in front of it. So write that as 1 point bits. In this case, that works out to be 1.10010. And so to get the fractional value, we take the fractional bits and we put a 1 point in front of it. So to convert this number into base 10, there are a couple ways to do it. The most straightforward way is to say, well, we obviously have a 1, and then everything to the right of the decimal point is a fraction. So I'm just going to take the raw value of those bits, 10010, convert that to a base 10 number, so that would be 16 plus 2, or 18, and then divide it by 2 to the n, where n is the number of bits that I had after the point, so 5 in this case. 2 to the 5th is 32. So if had my fractional bits been 1.00111, converting that to base 10 would have given me 1 and 7 over 32, because 00111 in base 2 is 7 in base 10, and since there were 5 bits, 2 to the 5th is 32, so I get that fraction 7 over 32. And then since I had a 1 to the left of the point, I put a 1 in front of it. So that's my fractional value. In this instance, the example I'm working with is 1 and 18 over 32, or I'm going to write that as an improper fraction. So 32 plus 18 is 50 over 32. And we could simplify that, but I'm not going to for the moment. So to take those pieces, the exponent value and the fractional value, we now need to combine them by multiplying. So we need to take 50 over, so let's see, our overall value is 50 over 32 times 2 to the 2 squared in this case. Not c squared. We need to talk about what the exponent value is first in a bit more detail. So when we take the bits, we take the value called the bias and subtract it from the value of the bits. So if the value of our bits was 2, we need to subtract the bias from that. Now the bias is another important value that's you just have to know for this representation. If we have 3 exponent bits, we say that k is equal to 3, and the bias is always equal to 2 to the k minus 1 minus 1. For our example, since k is equal to 3, that's going to be 2 squared minus 1, which is 3. But that will change anytime you use a different number of bits, and specifically a different number of exponent bits. So to convert my exponent bits into the exponent value, I need to do 2 to the bits minus the bias. Let's see, I'll leave this exponent bits as 2. And so, again, in this case, looking up here, our bits were 0, 1, 0. That was our exponent bits. That's a equivalent of base 10 value of 2. 2 minus the bias of 3 is -1. So in this instance, we would have 2 to the -1 power, or 1/2. And so down here, we need to take that same thing, 2 to the -1. So that's 50 over, oops, that's 50 over 32 times 1/2, which is 50 over 64. Now looking back to the sign bit, we had a 0, so this is a positive number, and so our overall value is 50 over 64. I'm going to delete this example, or this other bit here, since that wasn't part of our example. So those are the basic rules for a normalized number. Let's do another one. Let's convert another value. So I'll just write 1, 1, 0, 1, 1, 1, 0, 1, 1. So again, we'll start with the exponent bits, and we extract those. Again, with the sign bit, we can ignore for the moment. We have 1, 0, 1 is the exponent bits. 1, 0, 1, which is equivalent to 5 in base 10. So when we subtract the bias, 5 minus the bias is 5 minus 3, we get a value of 2. So our exponent value is 2. Now we take the fractional part, so that's fractional bits. We have 1, 1, 0, 1, 1. So to convert that into the fractional value, we have 1.11011. So that is equal to, that in base 2 is equal to 1, and now again I've got to convert 11011 from base 2 into base 10. So I get 16 and add 8 gives me 24. Skip the 4, so I add 2 to get to 26 and 1 more to get to 27. So that's 1 and 27. And it's still going to be over 32 because we have 5 bits. 2 to the 5th is 32. So 1 and 27 30-seconds. And again, I'm just going to convert that into an improper fraction. So add 32 to 27 gives me 59 over 32. And so now my overall value, my sign bit, if you look back up there, the sign bit was 1. And so this is going to be a negative value. Here were my exponent bits, here were my fractional bits. Oops, I think that just accidentally dragged that. So my value is going to be a negative number. It's negative 59 divided by 32 times, and now I need to take that exponent value, times 2 squared. So that is, again, negative 59 over 32 times 4, and we can simplify that as negative 59 divide the 4 out of 32, and that gives us 8. So it's negative 59/8 is our final value for 1, 1, 0, 1, 1, 1, 0, 1, 1. So those are the normalized numbers, and most of the numbers we use are normalized numbers. Let's look at the denormalized numbers. So these are similar in some way, but now since the exponent bits are all zeros, the exponent value is fixed at 1 minus the bias. So our bias again is 3. That was this for 3 exponent bits. We take 2 to the 3 minus 1, and that gave us 3. So our exponent value for this representation is always going to be negative 2. And that's based on the number of exponent bits that I have. So let's get a value to work with. So go 0, 0, 0, 0. Those 3 exponent bits being 0 is what marks it as a denormalized number. And then we'll just do 0, 1, 0, 1, 0 for our fractional bits. So for the fractional part, again we have the bits, which are 0, 1, 0, 1, 0. To convert that into the fractional value, we put an implicit 0 point in front of it. So for normalized numbers, we did an implicit 1 point. For denormalized numbers, we do an implicit 0 point. And then converting it to base 10 is the same. So this time I have 0 in front of the point, but after it I have 0, 1, 0, 1, 0. And converting that into base 10, just treating it that as a standalone number, would give me 8 plus 2 is 10 divided by 32. And again, the denominator is 32 because there are 5 bits, and 2 to the 5th is 32. So my fractional value is 10 over 32. So my overall value is going to be, let's see, I check the sign bit again. This is positive. So it's positive 10 over 32 times 2 to the negative 2, because that was what our exponent value was for all denormalized numbers with 3 exponent bits. It's always going to be 2 to the negative 2. So that's 10, oops, that is 10 over 32 times 1/4, which is equal to 10 over 128. That's 32 times 4 is 128. And again, we could simplify that further. I guess in this case it's just 5 over 64. But that's the end result for a denormalized number. So to review, you recognize denormalized numbers because all the exponent bits are zeros. The exponent value is 1 minus the bias, and you compute the bias based on the number of exponent bits that you have. When you take the fractional bits, to convert that to the fractional value, you put an implicit 0 point in front of it, and then convert that to base 10. And so the overall value is the fractional value times 2 to the exponent value, which is 1 minus the bias, or negative 2 in our case, and then apply the sign. So if the sign bit was 1, we'd make this negative. So that was in contrast to normalized numbers, which you recognize because the exponent bits are not all 1s, nor are they all 0s. To take the value, convert the value of the exponent bits into a number and subtract the bias to get the exponent value. For the fractional bits in a normalized number, you put an implicit 1 point in front of it, and then convert that to base 10 in the same way. And then apply those. You take the fractional value times 2 to the exponent value and apply the sign bit. For the special cases, there are 2 special cases that we're interested in. The first is, and we determine what it is by looking at the fractional bits. If the fractional bits are all zeros, then we have infinity. And if the fractional bits are anything else, we have not a number. So not a number is a special value or series of values that represent something that's not a number. Not a number is defined to not be equal to anything, including itself. And so if you're testing for that, you usually have to do something. You can't ask if it's equal to not a number, because that will always say false. So there's usually some special function for testing if something is not a number. So note that we can have positive infinity and negative infinity. There are, again, a number of different not a number cases, but we won't go into them. But fractional bits all zeros in a special case means infinity. Fractional bits anything else means not a number. And to recognize the special cases, you look to see that all of the exponent bits are 1s. So that's a basic review of floating point numbers, and just kind of go reviewing the rules for them. I hope that is helpful.